All right, today we're going to start Chapter 10, Work, Energy, and Machines. Your question of the day today, and if you'll just write this at the top of your note page that you're starting, what is your definition of work? Okay, so go ahead and answer that first, and then you can go ahead and move on. So you can press pause here if you need to. So Section 1 is work and energy, and that's what we're really going to focus on today. So what is work? The definition that you need to know is that it's when you have a force that's applied through a displacement or over a specific distance. So this requires physical or mental effort. And the units you're going to see here with this is joules, and that's going to be represented by a capital J. So anytime we're talking about work, you're going to see 10J, okay, that's joules. So how do we go about finding work? Well, this is the formula we're going to be using. The one in your reference packet does not have cosine theta attached, but I do want you guys to take a look at this for future reference. So W, that's your work in joules. F, that's your force in newtons. D is your distance or displacement in meters. And then theta, that's going to be in degrees. That's some angle. Okay, so let's go ahead and try an example. Let's say that a hockey player uses a stick to exert a constant 4.5 Newton force toward a 105 gram puck, and it's sliding on ice over a displacement of 0.15 meters, and it's going forward. I want to know how much work does the stick do on the puck, and for these problems we're going to assume that friction is negligible. Okay, so friction doesn't matter here. So here's our formula, W equals FD cosine theta. We're just going to plug in 4.5 and 0.15, and again we don't have an angle here, so cosine theta just goes away, and when you go ahead and multiply those two numbers you should get roughly 0.675, and again you add J as your unit because we are talking about joules. So there are some practice problems in your iBook that I would like you to look at and do, and you can stop the video now and go do those, or you can wait until the end of the video and go back and add those in. But I do want that to be part of your note set today. So that's page 647, 1 through 4. Now continuing on, I want to give you another example. And this example is where we do actually involve that theta. So we still have the same formula, W equals FD cosine theta, but now we have more than that to plug in. So we have 255 newtons. That's our force because it says sailor pulls a boat a distance of 30 meters along a dock using a rope that makes a 25-degree angle with the horizontal. How much work does the rope do on the boat if its tension is 255 newtons? So again, 255, that's our force, 30, that's our distance or our displacement, and then our angle in this case is 25. So when you plug all three of those in, you should get roughly about 6,933.25 joules. So pretty straightforward, just multiplying here. You could rearrange. I could give you the work and you have to find the force or the distance or even theta, but I won't ask you to find theta for this course. There are some practice problems that involve the cosine theta portion of the formula. That's page 649, so just a couple pages over, and it's 5 through 9. So again, you can either stop the video now, or you can go back later and do these once we've completed the video for today. Alright, energy is the other thing we want to talk about. Energy is very important for this class, and we're really going to get into energy in chapter 11, but just a brief overview, it's the ability of a system to produce a change in itself or the world around it. It's the act of being active or acting out something. So it's an active thing. And we have what's called the work-energy theorem. Just like we had the momentum-impulse theorem, there is a law of conservation that goes with this. So any work that's done on a system has to be equal to the change in the system's energy. So we're saying that the work that you do is equal to the change in the energy that occurs. Okay, so the work you do is equal to the change of energy that occurs. And that's going to be important for power. Okay, you guys know what power is. It's our electricity. It's how we plug in our phones, right? It's all of that, but it's a rate of energy transformation. So how do we transform energy from one state to another, from one type of energy into another? And the unit is watts, okay, just like your light bulbs, 100 watts, 60 watts, 13, whatever. And there is a way to find power. Power is equal to the change in energy divided by time. Or we can say the change in energy, or the change in energy is equal to work. So it could be P equals W over T. Okay, so P is power, that's in watts. E, that's your energy, or again, that's your work, but it's in joules. And then T is your time in seconds. Now, because we are talking briefly about power, your homework assignment tonight, and this is what I want you to do and have in for tomorrow, go home, ask your parents if you can bring in your power bill. It doesn't have to be the cost, just I want the portion that shows your expenditures for this month and your expenditures for last month or last year. That's what I want you to bring in. So if you've got that from Duke Energy, please go ahead and bring that in tomorrow. I will give you some extra credit points for doing that. So let's go ahead and use that formula. We have an electric motor that lifts an elevator 9 meters in 15 seconds. It's by exerting an upward force of 1.2 times 10 to the 4th newtons. So I want to know what the power does, or what power does the motor produce in kilowatts. So be careful there. So here's our formula. P equals delta E over T, or the change in energy. Well, we don't really have change in energy. But if you remember, we just did work. Work is equal to FD cosine theta. So all we have to do is substitute in FD for our change in energy. So P equals FD over T. And if you plug all of those numbers in like you see here, please make sure you use parentheses. That's going to be very important, just like it has been for the entire semester. You should get roughly 7,200 watts, but I asked you what it was in kilowatts. So when you move your decimal 3 places to the left, you get 7.2 kilowatts. And there are some practice problems I want you to do with this. It's page 655 in your iBook. It's 10 through 14. And again, include all of these practice problems in your note set for today. And that's it.